Hi, in this video we will learn about a class of matrices called elementary matrices. As the name may suggest, these matrices are related to the elementary row operations, and as we will see, these matrices will can implement the row elementary row operations by matrix product. Okay, so let us start by the definition. An elementary matrix is a matrix obtained from an identity matrix after applying a single elementary row operation. Well, for example, if we have 2 by 2 identity matrix, we can apply, well, any row operations you like. For example, we can multiply row 2 by a negative 2. Then we will have a 1, 0, 0, negative 2. Or we can do the operation, elementary row operation, in which we interchange row 1 and row 2. This will give us 0, 1, 1, 0. And this guy here, we can, for example, do 3 times row 2 added to row 1. So this will give us 1, 3, 0, 1. So these are examples of elementary matrices. Well, sometimes this is not your book's notation, but I will use this notation just to emphasize that this elementary matrix obtained by this elementary row operation, I will put it here as index, so like that. Or here it will be E of R1 interchange R2. This one would be E of R1 plus 3R2. Yeah. Well, why are these guys important? Why elementary matrices? Well, these matrices have very good property that basically they turn the elementary row operation as product of matrices. In other words, if you have a matrix A and you do apply an elementary row operation, say just one elementary row operation, then the result can be shown is equal to the elementary matrix corresponding to this elementary row operation times A. The operations that we have been doing just line by line, everything very ad hoc and by hand, now we can realize them as product. Let's see this in an example and then I'll write the theorem. So the example is, well, let A be this matrix 1, 2, 3, 4, 5, 6. Yeah. Then, well, I can do different row operations on this. For example, we can multiply row 2 by negative 2. Yes. So this will be 1, 2, 3, negative 8, negative 10, and negative 12. And what happens here is this guy, this matrix, can be realized as product of this elementary matrix and the original matrix. How? Well, just take the elementary matrix corresponding to that elementary row operation. In this case, it is here. Yes, we just found it. It's 0, 0, -2, and multiply to the original matrix. As you can see, when you multiply first row to the columns, they don't change first column. It's just one multiply the entries of first column. But when you multiply the second row to the columns, each one of the entries of the second row will be multiplied by -2. And similarly, if you interchange row 1 and row 2, you will notice that this is same thing as multiplying these guys together. So this element corresponding elementary row operation. So if you multiply, you get 4, 5, 6, and then 1, 2, 3, and so on. So in general, this is a theorem, a fact. Let A be a matrix, and then by M matrix, then every elementary row operation applied on A can be realized as product of corresponding elementary matrix and A. Well, as I wrote above, so what this says is that if you apply an elementary row operation, anything you like, this will be the same thing as you multiply the corresponding elementary row operation, elementary matrix of the elementary row operation to the matrix A from the left. Well, this has very nice implications for us, especially when we are trying to prove the fundamental theorem for the invertible matrices. But all of these things will work because of another simple property or fact about the elementary matrices. So this is another theorem I like to write as a fact that every elementary matrix is invertible and its inverse is another elementary matrix. Well, proof of this is easy, especially with the notation we chose here. Well, let's say we have an elementary, an identity matrix. We generate an elementary row operation. Let's say what? We do multiply a row by I. Then what we generate here is that, well, if you do identity, apply the identity, this will give us E of CRI, yes. Now, since we are assuming that C is non-zero, we can do, we have actually another row operation that if I apply on this guy, I will get back to identity. Well, we multiply the whole row I by C. Now this time if we multiply it by 1 over C, we will get back to identity. Yes. But what does this mean in terms of the theorem we just mentioned? This is an elementary row operation and this is a matrix, yes? So this can be written as the matrix. In this case, let me just write it A here, ECRI multiplied to E, the corresponding elementary matrix of this operation. What we show here is that, okay, this guy multiplied to that guy gives us identity. And this is a starting point that's saying, okay, very nice, this guy needs to be invertible. Okay, we have to check the other way around also, but in this case it will work. And what we showed here is that this guy is inverse of this. So ECRI is invertible and its inverse is E1 over CRI. The similar computation would show that, for example, ERI RJ, interchange this, it's invertible and it's inverse. Well, if you switch two rows, interchange two rows, you can switch them back and you get identity. So this means that the inverse of that is exactly itself. And well, if you multiply, if you add a multiple of a row to another row, then you need to subtract the same multiple of the row J from row I. So this is basically the proof that I was trying to say. Okay? So every elementary elementary matrix is invertible and its inverse is of that form itself. So it is an elementary matrix. We will use this elementary matrices when we're trying to work with the different notions of invertibility.